Salt Lake has become a center, a real hub for neural engineering research, I think because the bioengineering department has had historically a strong focus area in neural interfaces. Going back to the days of Dick Norman first started playing with the idea of multi-electrode silicon probes, which eventually became what we know today as the Utah electrode array. And there were a number of students that had gone through the department there. BlackRock Microsystems was started as a spin-off from Dick Norman's lab with a little company called Bionic Technologies. That grew, they became acquired as Cyberkinetics, and eventually they became BlackRock. Today, our company, Ripple, we're not a spin-off from the university. We sort of, though, had several of us that had gone through the bioengineering department in Dick Norman's lab. I had a friend who was in that same lab who had done work there, had worked at Bionic Technologies, and there were three of us that decided to form our own company, independent from the university, but we really wanted to focus on both neuroscience research tools as well as implantable neuroprosthetic devices. In particular, we wanted to focus on medical devices for humanitarian applications.
Interesting. So you founded the company. When was this?
This was back in about 2005. Yeah, so we've been around for about 12 years now, just a small group. We really had this sort of dual purpose of building research tools and developing implantable medical devices. Sort of the idea was that building tools would give us access to investigators who had new good ideas on medical therapies, and then medical tools that we would develop for human clinical markets would also be useful to investigators as well.
Interesting. And so I'm curious, how was this, like growing it and everything like this? The beginning years must have been very painful.
Yeah, sure. It's hard to start any new technology company, but in particular, we had, I think, really tried to learn lessons from other groups that had, especially in the implantable neuroprosthetic area, tried to develop technologies for humanitarian applications. Traditionally, technology development is done through investment from venture capital. However, we've seen lessons that this just really isn't a great model for developing humanitarian applications, that the markets are just far too small to support that kind of long-term investment that's required for those kinds of devices. So the idea was that we would have sort of a short-term revenue generator in our research systems tools. There's no regulatory overhead for those kind of systems. And then we would apply for federal research grants from NIH, DoD, DARPA to support development of new technologies. So that was sort of our idea for starting the company. And we've been very lucky in receiving quite a few awards now, federal research grants from NIH, DoD, and DARPA to develop this technology.
Interesting. So if I understood correctly, you kind of did the information side of things because it was not regulated, information processing, and then use that to jumpstart the rest of it, something like this.
Yeah, if we could build a small core of engineers and build a business that's sustainable around research tools, that we could sort of, keep the lights on for a company while we try to develop these much more expensive systems to develop these implantable medical devices, was the idea. And it's been a good ride. We've tried to be pretty conservative about trying to grow slowly and really build a core, strong team of engineers along the way. We had been a small company for several years. For about 10 years, we had been about 10 people. And a couple of years ago, we were selected to be a systems integrator in the DARPA Haptics project, which allowed us to jump up to our current size of about 25 employees. We're a little bigger now and really kind of focusing on getting these medical devices into first-in-human trials. And we were able to build tools that are now things that we're selling here at the Society for Neuroscience meeting for neuroscience researchers.
Mm-hmm. Yeah, the soft implants, everything like this, right? That's cool.
Yeah. So we've worked on a few kind of core technologies. Our flagship product here at the Society for Neuroscience meeting is our data acquisition system. So we have a system that's capable of a relatively high channel count, stimulation and recording kind of experiments. We have a modular system that allows investigators to go from 32 channels up to 512 channels of stimulation and recording. And our system, we're really kind of trying to fill this niche of investigators who want, in particular, a programmable system that's portable. So we've made a very, very small data acquisition system that can be actually worn by subjects in the lab and outside the lab. So we've really hardened this for sort of take-home kind of experiments. So this is our new Grapevine Nomad system, and that's capable of doing up to 512 channels. And the new feature that we're offering at SFN this year is that a lot of investigators have their own like closed-loop feedback kind of experiments that they want to do. They want to take in a little bit of data, process it really quickly, and then send some sort of output, either stimulus or other experimental instrumentation. So it's now possible for investigators to compile their own MATLAB code and run it on our hardware. So you don't have to be tethered to a computer anymore. You can have subjects really walking around with this system. This is also really starting to become really useful to primate researchers. Really kind of want something that's small, something that primates can actually wear. And so we now have a data acquisition system for that.
So how small is it? How wearable is it? How heavy is it as well?
Yeah, it's... well, we can look at the actual specs on the website, but it's quite a bit smaller than our previous neural interface processor, sort of our first generation system that had been out for about 5 years now. So we've really tried to make it a little bit smaller, a little bit stronger. It has onboard data storage and Wi-Fi capability and an onboard battery for these kind of portable applications. So that's sort of the core system. And then we've developed a couple other technologies. You mentioned the electrodes. We've been playing around with building polymer electrodes, conductive polymer electrodes. Basically, the idea is we take an implantable grade medical polymer and we mix in tiny platinum flake into that polymer and mix it up like an ink. And we have essentially a 3D printing robot, and we can print a multi-layered structure. So first we print a non-conductive layer of the polymer, and then we take the same polymer mixed with platinum dust and print traces and electrodes, and then sandwich that on top with another non-conductive layer. So you get an electrode that really has some fantastic properties because essentially it's all made of the same polymer. So when it cures, it's all one copolymer block. So traditionally you have problems with thin film polyamide kind of electrodes that you have different materials, and over time you have problems with delamination. But because this is all one polymer, it becomes very, very, very durable. So we've done accelerated lifetime flex tests with this polymer, and we found that we can get up to 70 million, 100 million flexions with these devices without having breaks. By having a multi-layered structure, we can get finer and finer features in a system by essentially stacking the conductive layers on top of each other. So that's a really interesting technology. We're starting to look at a few implanted medical applications for this electrode approach. And then finally, the third core technology that we have here is our implantable wireless systems. So this is a little bit more towards our medical device development. In particular, we're working on a device for patients with transradial amputation. It's an implanted system that listens to muscles in the residual limb and sends those signals out wirelessly to a little transceiver that's mounted in the socket. Basically, the idea is that these muscles are still innervated by neurons from the brain, from motor cortex, and patients can contract those those muscles in ways that they used to control their hand. We detect those contractions through these implantable EMG electrodes that are under the skin, and we send these signals out, and so it allows patients to have really independent, simultaneous, multi-degree of freedom control of a prosthetic limb. So this is something that we've been developing for about a decade now.
Wow.
Yeah, my goodness, it takes a little while when you're trying to develop these things through federal research grants. But we've had really tremendous support from NIH and DARPA to build the system. So now we're looking at finishing up final preclinical testing, and hope to be doing first in human testing really soon with this medical device.
Okay, wow.
Yeah.
Cool.
And so now we're making the wireless devices available to researchers here at SFN. We have a few customers now that have implanted them in non-human primate subjects. A real trick with trying to do research with primate is that percutaneous connection. Monkeys, they monkey with those things a bit. And if we can find ways of getting signals out without requiring that percutaneous connection, it really makes those experiments a lot more stable, a lot more doable.
Longer lasting.
Yeah, exactly.
Well, exactly. We were talking to a patient earlier today, and it was that's the reason that it was able to last so long for him, is because he wasn't monkeying around with it.
Sure.
He wasn't like banging his head against the cage or whatever.
Yeah.
Maybe throwing around the same amounts of food.
Yeah. Well, we don't want to, stop people from doing these things. Yeah, that's right.
So I have a question too about the implants that you're developing. I mean, what's the impedance look like for that? I mean, it sounds like if you're having this kind of platinum ink, that could be kind of high resistance. Right?
Yeah, so that's something that we had to play with for sort of a long time now. Yeah, we've been working on developing this ink for a bit. There's a trade-off that we want electrodes to be really, really malleable. We want them to be flexible. We're able to print them in such a way that they're very thin, and so we want them to drape, really nicely to conform to the surface of the brain. But at the same time, they need to be conductive. So we've really had to balance out how much platinum, that we're putting in the system, and that's still sort of an area that we're really kind of titrating to optimize. We have a few things that we can change to look at that conductance. The actual size of the trace that we use, if we're able to print it a little bit larger, we get a little better conductance. Also, again, the amount of the concentration of platinum that we have can change to make a few different levels of impedance for those electrodes. Yeah.
Okay. And also the question about the data acquisition products that you have. So I think BlackRock and Neuronexus have similar things. What's the advantage of yours versus theirs?
Yeah, so there are a lot of good products available for researchers in this sort of field of doing electrophysiology. We really wanted to sort of fit this sort of niche. In particular, there are a few things that we've really focused on. One of them is the capacity for doing stimulation. We have head stages available, small digital front ends that we have chips inside that are capable of doing both stimulation and recording. So any one of your channels can be used to record or to stimulate. And then we have added special fast settle features, so it's possible to stimulate and then very quickly start recording again to really sort of get rid of that stimulation artifact. So that's a feature. Also, our programmability is starting to be a thing that customers are really looking for. Being able to compile your own code to run on the box to really, again, drive down those latencies is a big factor. And I think finally the portability of our system, that our new Nomad system is really quite small. And so it's not just being able to allow subjects to sort of roam freely, but a lot of customers have a rig that they want to use in their lab, but then they need to take it into the OR. And so instead of having to deal with the hassle of getting a big rack-mounted system, wheeling it through the tiny little hallways of university medical centers.
A few kilowatts of power.
Yeah, Exactly. Instead, if you had a little battery-powered system, you can throw it in your backpack, bring it right into the OR, and get ready to go. Yeah, it makes this a really versatile tool.
Cool. Yeah, sounds really good. Sounds like you guys are on the forefront, the stealth mode, coming in and slowly, potentially taking over. Pretty cool.
Well, I think this is definitely a growing area. I first started coming to SFN about 15 years ago. Yeah, and there really weren't sessions for neural interfaces. I think really strong funding from our federal government has really made provided a lot of resources for more labs to grow and new labs to be founded. So there are a lot more researchers in this area than there were a few years ago. And I think individual companies are kind of finding, their own little specialties of customers that they want to try to work with. There are groups that are really terrific at like small animal systems that are really economical for doing a few channels in like mice and rats. There are other groups that are really focusing on optogenetics. And we're kind of in that primate and human subject research area.
Okay. Right.
Yeah.
Is there anything that we didn't cover that you want to mention?
Well, I guess I'd like to encourage neural researchers that to keep going in this field. That it is exciting to see how much it's grown recently, and to maybe put a plug in that industry is a pretty great place to be.
It's not the dark side, right?
Yeah, no, I think it's really pretty motivating that we get to every day we get to talk with customers, have cool ideas for experiments, and we get to be a part of coming up with solutions to help them do their research, and as well as building implantable medical devices, in particular for humanitarian applications, is really a motivating thing to do. Our goal is to try to get things to build new therapies for patients, and while discovery is exciting, there's something that's I think really motivating about development. To try to really get therapies out that are going to make a difference in patients' lives.
Yeah, exactly. In this way, you're not limited by grants or bounded by grants, but more by the customers, I guess, their grants. But that's businesses solving other people's problems, right?
Yeah, that's right.
Yeah. Cool. Well, thank you so much. This has been excellent.
Yeah, thank you.